The first question we're looking at is defining the term algorithm. The term is made out of two main parts. One of the parts is a set of instructions would be the first part, so a set of instructions, and the second part, to solve a goal or task. Or to achieve. To achieve a goal or task, Beautiful. On this one over here, these are kind of the computational thinking questions. There's abstraction, decomposition are two of the main computational thinking ones, but there are other terms that we care about. Abstraction, Mohammed, is when we do what?
It's the process of removing unnecessary detail.
Absolutely. So abstraction is when we focus on what's important, so we have to remove unnecessary detail. Data type, so all data in a computer is stored as what? Zeros and ones inside a computer. And sometimes those zeros and ones could be text. Sometimes those zeros and ones could be an image. Sometimes those zeros and ones could be a number. How do we differentiate? We have data types. If the data type says string, we know those zeros and ones mean that they are a text. If the zeros and ones are an integer, we know they're numbers. Decomposition. Decomposition is when we do what? Beautiful. So decomposition is not just for computing. You have a big complex idea that you're trying to solve. In trying to solve it in one go, you break it into smaller pieces, which you might break down again until they're small enough for you to individually solve. You solve all of those smaller items, and then suddenly you solve the biggest one. Efficiency, what's that all about?
Efficiency is how useful it is.
Well, in here, we're saying an algorithm is a set of instructions to achieve a goal or task. Linear search, binary search. What is the goal of linear search and binary search? So if you just use this broad term, the algorithms, do they do the same thing? Are they both a set of instructions, and do they achieve the same goal?
Yeah.
Absolutely. That's why you learn about linear search and binary search, because they are different in terms of efficiency. Which one is more efficient?
Binary search.
Binary search, right? Especially when what? The larger the number of items, the more efficient it will be. So efficiency is about achieving the same goal, but with using less instructions to get there, or less times you have to actually do fetch, decode, execute cycles. Input, that's about data being inputted into a system. You can think of that in terms of the hardware, like a keyboard or a mouse, an input device, or you can think about that in terms of the variable name equals user input to store that thing going in. So, breaking a problem down into a number of smaller subproblems, that was C, that's decomposition. The process of removing unnecessary detail from a problem, A, that's abstraction. And then finally, defines the range of values a variable may take, is what, sorry Matt? B. Yeah, it's B, because it's saying that sometimes it could be an integer, sometimes it's something else. Fantastic. It's worth saying, you've actually got the mark scheme on the next page, and the reason for that is it's not every question's like that, but for the sorting and searching, because you want to be precise with those definitions, I'll put it there for you. Do you remember how a linear search works? Now, let's say we had a list of items. I'll just draw you a list here. In this context here, I have this list of items, 19, 4, 13, 7, 5. If I wanted to use a linear search, where would I start?
From the start.
So, number one, that's the point we're going to go in here. Start at the first item. What should I do when I get to this first item? What am I doing?
Compare it with the search term.
And we don't have a search term right now, so why don't I just interject one here? I'll say that we're looking for...
5.
Well, I picked 3 already, but I would have gone 5. I have to go. So what do? We say that we compare the item to the search term. So that's the next thing we're going to say. Now, if we compare it to the search term, one of two different things are going to happen. What are the two different things we could have happen, guys?
It can either be the search term or not be the search term.
It will either be the search term or not. What computational concept is that when you could go one way or another? It's that you...
Selection.
That's very good, Mohammed. Selection. So you say, if they match, then I guess you found it.
Or
Else, you go on to the next one. Yeah? So compare. So we'd say, if they case, we start here, our search term is 3, we start at the beginning, 19, it's 3, 19, no, therefore we go to the next item on the list. And we're going to keep doing that. So we're repeating that. Now, what concept, Ayub, is it when you repeat things, when you loop things? Wait, it starts with I. Iteration. So when we're looping it around, it's iteration we're doing. You don't have to include this in your answer now. I'm just trying to link it to this concept. Until one of two things are going to happen. What are the two things that could happen? If you don't find it, what's going to happen? If it's not in the list, and you get right to the end and you haven't found it, it means it doesn't exist, yeah? So, if you've got to the end of the list, the way you have to write it is, let's say you use a for loop. So imagine there's an invisible index here, where let's say it's at 0, 1, you see that? 2, 3, 4. The way you'd write it, if I'm using iteration in programming, what would I use to do iteration? For loop you could use. So you could say for position 0, going up to what position? Faraz? Look on my board. So I'm going to start for C equals 0 up to what position? 4. See? So it'd be 4, and then you go 0 will become 1, 2, 3, 4, and it won't repeat back because you're going from 0 to 4 in that for loop, yeah? Okay, now we're looking at a binary search. Sometimes it asks you to describe how it works. That's like the last question. Sometimes it asks you to actually do it and show it in action. This time it's asking about sort of showing us in action. So state the comparisons that would be made. So i.e. which one of these are you going to compare if the binary search was used to search for the value 30. So to do this question, we're going to have to remember how binary search works. So with linear search, we start the first item, we compare against the search term. If they don't match, we continue and we keep looping until we either find it or not. Now, how did binary search work different? Binary search finds the middle item. So if we're saying it finds the middle item, we're going to have to look at our list of items here and then determine which one is the middle item. So in here, which one is it going to be?
21.
Yeah, so 21 is right in the middle. Remember, sometimes it can be an even list, so you'd have to go middle left. But in this case, we don't. So the first item is going to be 21. If I'm being honest, it might be worth, so that you're careful, you might have to describe it as well. So you'd have to say something along the lines of, find the middle item in the list for a binary search. In this case, it would be 21. And then what do you do?
And then you would compare it to 30.
So you compare it to 30.
Check if it's higher or lower. If it's lower,
Bingo. So you check to see if it's higher or lower. 30 in this case is higher. And as you say, everything to the left, do you also get rid of 21? Yeah. Absolutely. So all of that goes. So that's all gone now. And then what do you do? Absolutely. In the new list, you find the middle item. Well, it's position 5, so the number would be. And then the question would be. Well, because, Matt, so 30 is lower. So therefore, you want to discard to the right. Do you also discard 31? Yeah. Bingo. So what do I have to write down here next to 21 then? So what the next item? So what item should I write down? So what item am I going to write? So I wrote down 21 as my first comparison. What's 31's the next one, isn't it? Because that's the one I'm actually comparing. Whoops. Let's change. So 31 is my next item. And as Matt correctly identified, 30 is lower than 31. So therefore, we're going to discard to the right and inclusive of that item. And then our last position, so then the last thing we'd write down is what? 27, because 27 will be our last item. Oh, the whole thing's broken now. Oh well. So the last item would be 27. Now, yeah, and then the item wasn't found because we're saying, is it higher or it'll be? Is it lower than 27? No. Is it higher than 27? No. Is it this? No. So it's not item not found. See these 3 marks. It might be worth your while to actually describe it though, to say find the middle item, do the comparison. I haven't in this case, and the marks would be for 21, 31, and 27. So last question's here. for a binary search algorithm to work correctly on an array of integers, what property has to be true? Faraz? Must be in order. Must be in order. So for this one here, it must be ordered. Is there a big advantage of using binary search as opposed to linear search? Yes. It's much more, what was the word again, beginning with E? Efficient, especially when there's a large number of items. However, the list must be sorted, and therefore it's often worth sorting an unsorted list to then allow you to use binary search. And we learned about two sorts. What were the two sorts we learned about? Bubble sort and merge sort. Now, this one here, in this merge sort, half of it has already been done for you, the demerge bit, split it into separate pieces. And now it's just the merge bit. Now, bear in mind there's 3 marks for this. I think these are some of the easiest 3 marks you could ever have. Think about what's happening. These ones are coming together here. And when you merge these sections together, it's called a divide and conquer algorithm. You just merge them in the order. Now, does it say whether it's ascending or descending? Does it say? Oh, that's a good point, yeah. But the default, if they don't say, assume it's ascending. So in here, you've got to put it in here in ascending order. So what are you going to put here and here? Bingo, Saeed. 3 and 7. The next one? 1, 4. The next one? 2 and 8. Exactly, doesn't need to be switched. The last one? For this last one, this one and this one are coming together. And you see the reason why merge sort's so efficient is it's partially sorting it into smaller pieces, and then it makes it more efficient as it goes along. So let's look at these items here. What am I going to write out first? 1, and then...
1, 3, 4, 7.
Yeah, exactly. So to be candid, I was saying to you earlier, these are some of the easiest marks that you can get. Oh, and here it's 2. And then finally, these are being merged together to make these. The arrows, I don't think are strictly necessary for you to do. I'm doing that for descriptive purposes. There's 3 marks right there. Will you ever get an easier 3 marks?
No. Probably not.
State one advantage of the merge sort compared to the...
Can you just talk about it in the figure 2?
Well, let's assume it's a bubble sort in figure 2, because that's the only 2 that you know about. So what's the advantage? What was the word? Efficient. Merge sort is more efficient. Merge sort is more efficient. Wait, what can you do? And you were saying, particularly when there is a large number of items to sort. So the larger the number of items, the bigger the difference becomes. If you're only sorting, say, in this case, 8 items, the difference between bubble and merge is non-existent. Bit there. Truthfully, you might get the mark for saying it's more efficient, but maybe you won't. So it's worth getting in here. So if it's a 2 mark here, you might say, when is it? It's same with a bubble sort, and same with linear search and binary search. When the number of items becomes bigger, the relative efficiency increases. Okie dokie. So now, this is the question that came from the November paper. So this is the one that people would have taken if they were not happy with their centre assessed grade last year, because there was no June paper. And I think what they've done is allows you to pick, because they're trying to take into consideration whether somebody had covered one topic or another. Truthfully, I don't know a single person who did that November paper, so what can you do? But anyway, in here it's saying pick between merge sort and bubble sort, and it's to demonstrate it. I'm actually going to do both, so that we get to see both in action. Which one do you want me to do first? Should we do bubble sort first, yeah? Let's do bubble sort. So let's remember so these are our list of items. Let's remember how bubble sort works. Now, do you remember I drew something to help you consolidate the idea of what I meant by bubble sort? Do you remember what I drew? Yeah, brackets around, the first 2 items. So I use the term drawing a bubble. Do you need to actually draw those brackets? No, but I'm doing that. Why am I doing that? To try and actually link the idea of bubble sort with the idea of having a bubble, right? Now, what do we do now? We've drawn it around 8 and 4. What should we do? Yeah, we have to look at it and then we say, are they in ascending order? Are they in ascending order? So therefore, what do we do, Ayub? Swap them. Perfect. Once we've done that, underneath it, what should I do? I should rewrite it again with those movements made. And then what should happen to this bubble? Shifts up by 1 to the right. Perfect. And then what's the question? Are they in ascending order? Therefore, we swap them over. I should write it out again underneath. So 4, then 1, then 5. And then finally, what should happen to this bubble? So it should be around 8 and 5. Are they in ascending order? What should I do? Swap them. And then what should I do? 4, 1, then 5, then 8. Have I? Thank you. I was going to ask the question, is the list now sorted? No, it's not. It's completed the well-remembered first pass. What has been established at the end of the first pass? The 8 is in the right position, right? So what should I do now? Reset. So where should I draw the bubble? 4 and 1, right at the beginning. What's the question? So we should switch or swap. 1, 4, 5, 8. Now at this point, technically you've finished. But what should happen is those two would compare 4 and 5. Are they in ascending order? Yes. So do you swap them? No. And then you finish the second pass. And then what happens is that 1 and 4 are the right way around and they finish. Now, let's say there were a long list of numbers, say 10, and you had the last 5 to do, but all 5 of them are actually in order. Does it seem like a bit inefficient to still have to compare them, even though you know that they're in the right order? Yes. So what they do is they have a Boolean flag, and it says, did you have to make a swap? If you didn't have to make a swap, and you went up to 0.6, then you stop the algorithm at that point, because you've proven if you didn't have to make a swap, then are they all in ascending order? Yeah. Yes, which means actually, if you did the algorithm on this, 1, 4, 5, 8, it will compare 1 and 4, did you need to swap? 4 and 5, do you need to swap? 5 and 8, do you need to swap? Stop, because you didn't have to make any swaps. Otherwise you'd have to go, okay, then compare 1 and 4, 4 and 5. You see what I mean? So that's a little bit of efficiency that's going on there. What's the other one we need to do? Now, we demonstrated half of merge. The reason I want to do the other one is because you have to demonstrate potentially the demerge, as in the separation into n number of sublists, and bring it back together again. And I want to just recap. So we're going to start with 4 items. What do you always split it into? What's the maximum number of things you can split it into? 2. So you can't split it straight into 4 ones. If you had a 5 number of items, what do you have to split it into? 3 and 2 or 2 and 3, absolutely. So in this case, I'll split it into 2. Then what would happen? 1. So now you've got n number of sublists. And then what's going to happen? Yeah, then do you remember I talked about it's like a mirror image the other way around? And then finally, they'll merge back into the 4. I'm not going to draw the arrows because I'm getting a bit conscious of time as we go along. This one at the top, what am I going to write in here? Bingo. Yeah, so on the left side, I'll write on this side, and then... All right. Yeah, at this stage, I'm demerging. And when I'm... Yeah, exactly. Which is, really the important bit of the algorithm is the merge bit, hence merge sort. So in here, I have to place it into this list in ascending order. So what do I write down here? 4 and beautiful. And on the other side, and then 1, 4, 5, 8. People, what was the advantage of merge sort over bubble sort? What is the advantage of merge sort? What's the advantage of bubble sort over merge sort? Correct, Saeed. The advantage of bubble sort over merge sort is that bubble sort can be done in the original array, while merge sort, you see here, we have to create additional space to do it in. So there's a need for additional space. So these are additional type of questions we can get on paper 1. For image representation, there are 2 what, Matt? The two factors that influence the quality of an image. Resolution's one. Bingo! So, resolution is the number of pixels. The more pixels there are, the sharper the image is going to look. Whereas color depth, anybody?
More color.
Yeah, you use more bits, therefore can show more colors. Pixel. Now, since I'm the one marking it, I'll give you a mark for this because I'm not sure if it actually is on it, but I feel you should get the mark for it. Do you know what pixel is short for? Picture element. It's the combination of those two makes the term pixel. Having said that, though, the definition they were giving you for is a single dot of color, which I've always hated as a definition, and now I'll accept it, but I can give you the option to do picture element. So a single dot of color. Anyway, now this one here, this is truthfully, and we probably experienced this on Tuesday, one of the main places where people go wrong is linking bits to the number of colors.
It's like positive.
That's exactly right. So in here it says, state the maximum number of colors that can be used if a bitmap image has a color depth of 6 bits. What can throw people as well? Sometimes say, if there's 40 colors, what's the bit depth of that? So as a reminder, on this side, we've got bits for color depth, and then on the other side I'll have the total number of colors, and we'll say, what should we say, 1, 2, 3, 4, 5, etc. If there's one bit, how many different, because either 0 or 1, so you have 2 colors. If there are 2 bits, 4. If there's 3 bits, 8. If there's 4 bits, 5 bits, 6 bits, 7 bits, 8 bits, 9 bits. Point is that this is the bit translating the colors or values backwards and forwards will get struck people. Can I also point out, if you wanted to store, say, 20 colors, what's the color depth if you want to use 20 colors?
5.
You have to use 5, exactly. If you use 4-bit color depth, can you represent 20 colors? No. So you'd have to use 5-bit, and then you just would choose not to use 12 in this context. So, what is the maximum number of different colors that can be used if a bitmap image has a color of 6 bits? Thank you, Rob. Go. I saw that you were paying no attention, so I thought, here's your opportunity. Be a hero, Rob. You are a hero, Rob. 64 colors. 64 colors. And never feel that it's not worth taking the time. You know, I talked about this with hexadecimal. Sometimes I'm like, okay, what's 13 in hex? I feel that's D, but what I'll do is I'll go 10 is A, B is 11, C is 12, D is 13. Do the same here. If somebody said, oh, there's 16 colors, I'm thinking 4 straight away. How long is it going to take you to go just to check? 2 colors, 4 colors, 3 colors, 16, right, 4. Right? Because that would be bloody embarrassing to get it the wrong way around. Because guess how many marks you get if you're off?
0.
Thank you, Matt, for your volunteering to answer the next question. What is the formula for calculating file size? Because that's the next one here. So for an image, file size equals something times by something. I'll give you a clue. They're the two things you said earlier. Resolution times by... Well, what you're saying earlier there, it's worth picking up. When you said sample resolution times by sample rate is for a sound file. This is resolution, which will come in useful later. This is resolution times by color depth. So, you know what I'm going to do? Let's go and try and answer this question. Abdali, what do you reckon we're going to do for resolution? What do we mean by resolution? What we mean is the total number of pixels. So what information do we have to get the total number of pixels in this case? Go on.
It says 800 by 1,000.
So 800 times by 1,000. That's quite nice, isn't it? That's going to give us
Big number.
800,000 in this case. And then times by color depth. Now, This is the one place we can easily trip up, isn't it? What is color depth? Do we times it by 20? But that would be easily done, wouldn't it? But you're exactly right. It's 5 bits, because 5-bit color depth is what we need. Nice one, guys. So times by 5 and times by 5. So the answer for this one is 800,000 times by 5. That will give us 4 million. Is that the answer we want to give? So we need to convert it into kilobytes. Shh. So first of all, we divide it by 8. Why do we divide it by 8? Because there are... No, why do we divide it by 8, the first one? Because there are 8 bits in a byte. So that's going to give us 500,000. Yeah, and why don't we put the thing now, bytes? Is that the answer to the question? There you go. So kilobytes is 1,000. So then we'd have to divide that by 1,000 to give us the answer that we're looking for, which is 500 kilobytes. How many megabytes is it? How many megabytes is it? If I wanted to express this same number in megabytes, what would I say? Anyone? So what is a megabyte?
1,000.
It's 1,000 kilobytes, so it's 1,000,000 bytes. So if it was megabytes, it would be 0.5 megabytes, right? Hey, what about 1 billion bytes? Gigabyte. And then the next one's terabyte. You don't have to worry about petabyte, etc. We're only up to terabyte. Next question here. It's all about sound representation, where image representation is based on 2 things: resolution and color depth. Hello, miss. Image representation, color depth, resolution. Sound representation, what are the 2 factors we care about? Do you remember?
I believe it was sample rate.
Sample rate.
Sample resolution.
Bingo. Now this diagram I'm doing at the bottom here, I'm doing it just to have a little bit of a reminder. That is a sound wave. What did I call that? Beginning with A. Analog. I said that the world that we experience is analog. It's smooth waves. When we want to record it in a computer, what do we call it? Digital. On this axis, what is this? Sample. Oh, sugar, I've done it the wrong. I've already done it. I've actually made a mistake. I've got it the wrong way around. I know. My apologies. This is sample rate on this side. And this side, thank you guys, I've got that recorded, so I appreciate that. Sample resolution. What we do, what is the process? The process is as we go around, we go along on this way, and we sample the amplitude of the wave as we go along. So maybe we sample here, and we go dot, 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 and we sample at this point, and then we sample again at the next point here, we sample it here. Do you see what you're doing? And then you're recording the level, the level over here. So on this case, on this axis, maybe it's 0, 1, 2, 3, 4, 5, 6, 7. If I've got 8 different values, what is the sample resolution if I have 8 values? So if I want to have 8 values, how many bits do I need? 8 values, how many bits do I need? If I had 1 bit, how many values can I make? If I have 2 bits, how many values can I make? If I have 3 bits, I can make... So this is a sample resolution, in this case, of 3 bits. Now, looking at our thing here, 3 is at this point, 2 is at this point. Is that at either 2 or 3? It's in between, isn't it? So if I want to actually demonstrate it, if I want to record it, I'll have to make a guess. I have to say, does it look closer to 2 or 3? 3 to 3. So what you do is then it goes up to that point. The next one here is 4. So we were lucky that time. So this one here, it's between 5 and 6. Which one does it look closer to?
5.5.
But which we can't do at the moment, so we'll say 6, fine. Now, do you see what's happening as I'm doing it? Does this look like a smooth wave?
Not really.
Does it look like a really blocky thing?
Yeah.
And what's happening is that as I'm going along doing this, because I've got low sample resolution, I can't accurately match it. And because my sample rate are not sampling very often, it looks like this blocky wave. The more often I sample it, do you see, the smoother it will become. But what else do I need? Bigger sample resolution, which will result in a bigger file size. So eventually it can look smooth like this. That's why back in the early 80s, when we had like 8-bit computers, were the graphics photorealistic? Was the sound like normal? It was just like bleep, blips and blops. And as time went on, and we had the Sega Mega Drive or whatever, 16-bit, and we had PlayStation 32-bit, the first one. PlayStation 2, I think, is also 32-bit. PlayStation 3, 64-bit. As time went on, what's happened to the quality? It's looked more and more like, what did I say that begin with A? Photorealistic, but it looks like analog, doesn't it? The sound becomes more like real sound. Yes, Ayo. Let's have a read of this question. Describe why the sound must be converted to a digital format before it can be stored on a computer system. So maybe first of all say that sound in the real world is analog. Sound in the real world is analog. A computer only understands zeros and ones. Therefore, we need to... What was the process when you're recording the wave? What was it called? Sample. Potentially, you could even talk about... You could expand it a little bit and even talk about things such as sample resolution and sample rate. On here, the next question is about using these things. The sound engineer is using a sample rate of 2000 hertz. A hertz meaning...
Frequency.
What does a hertz mean, though, specifically? Once per second. So 2000 hertz, meaning it is 2000 times per second. And a sample resolution of 4 bits. So every time it's taking this sample, it's costing 4 more bits. What is the minimum file size of a 5-second recording? And your answer should be given in bytes. So let's get the algorithm for file size. So sound size. The algorithm is, what is it? Sample rate times by bingo. Sample rate times by, what's the next thing? Sample resolution in bits. Last one is duration in seconds. Because of course, this is, the first 2 bits is saying how many bits there are in every second, then we times it by second. So, what is the sample rate? 2000 times by 4 bits times by 5. So that would be 2000 by 4, which is 8000, times by 5, so that's 40,000 what? Bits. Yeah, this is the one bit we can go wrong, and therefore, what do we need to divide by 8? So that would be 5,000 bytes. Now, do we write down 5 kilobytes?
No.
There you go, because it says it wants it in bytes. Yeah, we do as we are told. Beautiful. Super quick. The sound engineer currently uses a sample resolution of 4 bits, which allows them to do 16 different bit patterns. She wants to increase the number of bits from 16 to 32. So remember, this is the same as color depth, same deal. If you want to go to 16 to 32, there you go. You double, so you add 1 more bit, that gets you 5 bits, will get you 32. What would 3 bits get you? How many different values? 8. What about 8 bits? 8 bits will get you 256. 16 bits, 65,536. I know. I didn't do that in my head. I just remember the number. The next one, shade 1 lozenge to show which of the following correctly states the effects of increasing the sample rate. So let's go through them. Does it decrease the quality of the recording? Does it have no effect on the quality?
Of course it does.
Does it improve the quality of the recording? It does, but it has no effect on file size?
It does.
Because
D. It both improves the quality, but the downside increases the file
So, may I
size.
ask you a question? Why does this? Why do these papers have to be so fast?
This is the last topic. So, you know when I was saying paper 1, yeah, it's about pseudocode, but these are some of the other questions we can pick up as well. So there was like searching and sorting algorithms, there was computational thinking, decomposition, abstraction type questions, and data types, and then there were sound and image representation questions. We've also got logical circuits. Let me do this for you super quick. How many gates do we need to learn about?
Not and or.
We need to learn about 3. We need to learn about the AND gate, the OR gate, and the NOT gate. What do we need to be able to do with each of these 3?
Identify.
You need to draw them first of all. So the AND gate, let me give you the tip. When you're drawing it, draw it with a straight line there and then like an oval like this. How many inputs go into an AND gate? 2. How many outputs from an AND gate? 1. What do I do different with an OR gate to make it clear? Is that curve. So here, but this time, just make sure, if you get that curve rather than the straight, it makes all the difference. How many inputs go into an OR gate, Abdali? 2 is the answer, Abdali, you were looking for. Thank you, Ayub. How many outputs from an OR gate? 1. What about the NOT gate? Anybody remember? Triangle with a bobble at the end. 1 input, 1 output. And I'm going to label these up, right? Let's label these up. So we've got A input, B input, O for the output, A for input, B for input, 0 for output, A input, 0 for output. What's the other thing you need to do? Do you remember? Do you remember truth tables? So trace tables was when you trace how a variable changes through an algorithm. Trace tables are when you can go through an algorithm and trace how a variable changes. Truth tables are when you record whether it's true and false for logic gates and logic circuits. So we've got to evaluate the logic here, and there's actually one condition we really care about which is different to the rest. Which one's that for an AND gate? Absolutely. When they're both on, the output's going to be 1. Otherwise, 0. So that's the way to remember for an AND gate. It's only when A and B are on, then it's on. Otherwise, off. With the OR gate, it's 0, 0. Spot on, Ayub. So on this one, with an OR gate, the one you have to care about, if they're both 0, the output will be 0. Otherwise, 1, 1, 1. What's going to be different with the last truth table? Well, how many inputs have I got? 1. How many outputs? 1. So I've only got, what's the combinations? 0. So what's 0 going to do with a NOT gate? Hey, what's not 0? What's not 1? Beautiful, okay? So this is all you need to know to be able to do it, but then of course it's applying it. So let's come back here. Yeah, which one of these do we think it is? So we can look at it here and we can see that it's a AND gate. There you go, easy money.
So can I just quickly copy the table?
Of course you can. I'll leave that up, guys, if you want to have the opportunity to do that. I'll leave it up there for a sec for you guys. Let's evaluate this question. Now, immediately we might feel a bit anxious about the complexity of this question, but let's have a little read through. A partially completed logic circuit is shown in figure 2. Figure 2 is this. So this is a logical circuit. And what it's saying is that that's a, what kind of gate is that? NOT gate. But we don't know what the other ones are, and we need to figure it out. It detects if a computer has been set up correctly. So that's what this is. There are 2 keyboard input devices. Keyboard A, so that input there is keyboard A going in, and keyboard B, and that's keyboard B going in. Either one can be connected to the computer system. So either A could be connected or B. However, if they're both connected, so if A is connected, we represent it with a 1. If it's not connected, you represent it with a 0. So if they were both 1, it shouldn't work, right? If they were both 0, it's going to be a problem. You want 1 to be 0 and 1 to be 1, or 1 to be 1 and 1 to be 0. Okay, anyway. How if they're both connected to the computer will not work? Output P has the value 1 if either A or B, but not both. It's actually a specific type of logic gate called exclusive OR, which we learned about. Let me give you the first tip. This looks tricky, right? Bless you. Looks tricky. Can I give you the first tip? How many inputs are going into this? Whoops. One. There is one input going into L1. Which logic gates do you know? So L1 must be... So even without reading it, we know that. So that's not. L2 and L3 both have two things going inside, and does L4. So it's either and or. So it's one of the two. So now we have to figure it out. Now, people, here's what I do with a question like this, because trying to actually have a mental model of this can be quite difficult. I plug in real values. So if A is 1 and B is 1, should the system work? If both the keyboards are on, should it work? No. So what we're going to have to do is we're going to evaluate it. Now we know that this is a L1, what do we say it was? A NOT gate. So let's evaluate what happens. A goes in there and it's 1. So at this point, what will it be? What's not 1? 0. So far, we've got 0 coming in here and 0 coming in here. B is going to be 1 going into here. Yes? And then over here, it's going to be 1 going into here. Yes? So you've got two gates here. Now, if it was an OR gate, so this right now, this is us thinking it's either an AND or an OR. If it was an OR, what would the output be? 1. And if it was an OR gate here, what would the output be? 1. So if that was an OR or an AND, what would the output be? It doesn't matter. It'd be 1, wouldn't it? And do we want it to be 1 if both of them are on? Do we? No. So it can't be an OR. What happens if it was an AND gate? 0 and 1 will give you 1 and 0 will give you, and that could be maybe a...
So we need to make the top, the L2 and AND gate and the bottom one and not OR gate.
Well, I'm having to think for the moment. Am I certain right now? No. I'm going to test out what happens if we just plug these as both as ANDs, right? So I've got an AND here and an AND here. So let's think about it. Let's now talk about a time it should work. So what combination should I give it so it should work? 1 and... Yeah, well, if one's on and another one's not on, should we see what happens? Yeah? So let's go back here. Anyway, let's actually get the delete. So we're going to go through this again. So if I'm here, what is not 1? 0. And then the other output going into here is going to be that B. What is B? So it would be 0 and 0. And I'm saying if it's an AND gate, that will turn into a 0. On this side, I've got A was 1, and so that would be still 1. And that 0 will be flipped into the 1. What's an AND? What's a 1 and a 1 going to make you? What output should I get at the end here?
0.
So if I made that an AND gate, would it work? No. But if I made it a... Now, I'm not saying this is... You could actually do a bit more testing, couldn't you, with different values. But do you see what I've just done here? What did I do first of all? If it's a single input coming in, what's it going to be? A NOT gate. And then what did I do? I plugged it with real values to see and then test it out a bit. And so I think L2 and L3, what do I think it's going to be? No, look at L2 and L3. What are they? So and finally an OR. Now, so let's do this one again. So this one is actually easier. I'll tell you why. They've actually given you the Boolean expression. Do you remember a long time ago I said if you wanted to draw it, the first gate is the one that's more in the brackets, and then you work from the inside the brackets out. Remember this a long time ago?
Yeah.
So which gate is the most inside brackets? Not. And look at that one there. Single one going inside, so gate 1, what's it going to be? Beautiful. This one here, state the name of the logic gate used at gate 2. So now it's asking you to figure it out. Well, you've moved out of not. What do you reckon it is? Looking at these and. See? So that and is that one there. That and is that one there. And then the gate 4 is a... Perfect.
So does that mean gate 3 is the AND as well?
Yes, yeah, it is. Draw the logic circle symbol in the space below for gate 3. So what was gate 3? So what we're going to draw? Yeah, so straight line down, like this. What else? Am I finished?
2 inputs, 1 output.
I made a bit of a boo-boo there, a bit too much to the edge, a bit more in the middle. There you go. Gate 4, what do we think gate 4 was? OR. So what was the difference? Curved. You know, I'll be honest, that's still not a great picture, but as soon as you see that curve, I'll see that and I'll know you meant an OR gate. I see the flat line, I know you mean an AND. Right, not quite straightforward. This is the alternative. So before we did a truth table, but it was just for one gate, and now it's doing it for the whole circuit. So, first of all is this. You've got, this is the Boolean expression. It looks super complicated. This is the truth table for it. These are all the different inputs, and then what the output is. Asking you to think what the expression could be, and then to try and do this truth table. Here's what I'd like to do. Final type of question you can get for logical circuits. Sometimes you could be asked to draw out the logical circuit. You could be given a question like that and be asked to draw it out. In this case, we've been given a truth table and then asked to evaluate it. And a question like this, I just evaluate it one at a time. So the first one is not A1. So A1 is here. So if it was not A1, 0 would become 1. I mean, instantly you can see it's not working. A2 or A3. So 0 or 0 should make... No. 0 or 1 should make... 0 or 1 should make 1. So, yeah, but some people said 0.
I didn't know it said OR.
All right, guys, calm down. With an OR gate, if it's a 0 and a 1 going to an OR gate, it should be 1, and in this case it's 0, so it can't be B. Let's evaluate C. A1 and not A2. So A1 here is 0. Oh, what was the one condition with an AND gate when it was actually on? So in this case, it would be when A1 is 1 and A2 is 0. So A1 is 1 there, A2 is 0 there. So the output, so not 0, so that should be 1 and 1, should make the output should be... Let me do that again. For an AND gate, if both the inputs are 1, the output should be 1. So that means that A1 it should be 1, and because it's not A2, it's when A2 would be 0. Because that would be not 0, would be 1. So we have to look where A1 is 1 and A2 is 0. Because not 0 would make it 1. Yeah. So in here, do you see here, it's A1 is 1, A2 is 0. What's not 0?
1.
So that should be 1 and 1 should make 1. And is it 1? So that means that, is that one correct? So let's do the last one. A1 and A3. So in this case, 0 and 0 makes 0. But what was this with an AND gate, which is the one special case we care about, which is different, is when they're both 1. So A1 is 1 here, but it's 0 here. A1 and A1
There we go.
makes 1. 1 and 1 makes 1, and everywhere else will be 0. So which one's it going to be? D. So finally, complete the truth table for this expression. So we do it in stages. So first of all, it's X and Y. Essentially, this is getting you to remember your truth table for AND. So when it's 0 and 0, the output would be
0.
If it's 0 and 1, the output will be, if it's 1 and 0, if it's 1 and 1, 1. That's 1 mark, easy money. Next one, not X. So not 0 is, give me the rest of them.
0.
And then finally, this bit here, X and Y, or not X. Do you see that's X and Y, so it's that one.
0 and 0.
The not X is here, so it's OR of these two. Yes, so OR of these two. So what's this going to be? 0 or 1 will get you...
I knew that.
Because remember, with the OR gate, what's the one special case with an OR gate? Both 0, yeah. So actually, you could do this. You could say, it's this one down here is 0 or 0. That's the one time it happens. But let's go through it. 0 or 1 should get you 1. 0 or 1 is
1.
0 or 0. 1 or 0.